How's it going? Everybody doing good? All right. Halfway through the week, so that's good. Does anybody have any questions today before we get started? Homework? Project?
Is the trade-in value of a car, or is that like the private seller value of a car? That can be different.
You choose.
Okay.
Keep it consistent though, probably, right? I was thinking probably like a private party value, but there's no reason you can't use the trade-in value, I suppose. Yeah.
Does it have to be like that accurate, or can we go off like if I ask her, oh, what's the value of your car?
You can do it however you want.
Okay.
You can do it however you want. Yeah. Some people are probably more or less concerned with accuracy. Comes down to personality type, probably, in some ways. So, what else? Any other questions about that activity?
Did you say that there has to be a minimum sample size? Like 10 people, is that okay?
10's okay, yeah. Typically, in statistics, we like to see at least 30 for reasons we'll learn later. But 30 is a decent sample size. But the more the better. Yeah. Any other questions?
What's everybody's car worth?
What's everybody's car worth? Is this a random? That's not a very random sample, though, right?
It's a random thing.
That is a random.
Are you sure? What does random mean?
It depends what you're doing.
Our majors.
No, there is a definition of random, at least in statistics. What does random sampling mean? What's the definition? We talked about it last week.
Everybody has a chance.
Everybody has an equal chance. So if your population is CBC students and you sample everyone in this room, does everyone have an equal chance of being picked?
Well, we only need 30.
But is it random? But is it random, though?
I mean, it's technically random. You didn't pick the people who went into this class.
It's.
Everybody has an equal chance.
You say technically. You say technically. I think you're using that term incorrectly. It's technically not random. Does every student at CBC have an equally likely chance to fall into your sample if you only pick people from this room? Absolutely not. We've just ruled out 7,000 students from our possible sample by not allowing us to pick anyone out of the room, right? So it's not random. Yeah? Technically not random.
Our majors are different, though.
That's true, but is it random?
Yeah.
That could be one of the answers to how we could do this better next time.
That could be one of the answers. That could be one of your answers. Random samples are hard to construct. Yeah, they're difficult. They're very difficult. It's hard to get a random sample because of that. But yeah, remember the definition of random means everybody in your population has an equally likely chance of being selected. That's what random means. And if you constrict yourself to just say us, then we've automatically lopped off a huge chunk of students, faculty, and staff. Also, I said in there students, faculty, and staff. So you just lopped off all the staff and all the faculty from that sample.
There's you.
Right? There's me. I'm not very representative of I might not be very representative of faculty, though. Or staff, right? Could be. Anyways, something to think about. Yeah. So, I didn't say you had to take a random sample, actually, but that wouldn't be random. Okay. Not to mince words too much, but okay. Any other questions from the homework or anything? No? You guys making some progress on that, hopefully? Okay, slow and steady wins the race. Okay, you'll get there. Cool then we're going to go on if you don't have any questions. All right, so last time we talked, we were talking about some measures of center. We introduced this idea of summation notation, so hopefully you're going to be somewhat comfortable with that because we're going to use it again today. Again, remember the whole idea here is we have a population going on, and part of that population there's a parameter, right, that describes it, but we're typically looking at statistics from a sample. So we differentiate in our notation between parameters and statistics. We call the population mean mu. We call the sample mean x bar. And we did some examples of calculating means. The other thing we saw too with means and medians is that the mean is more affected by outliers than the median, so we call the median kind of a resistant or robust statistic. And so there's sometimes actually, in some cases, the median is actually a better measure of center than the mean. And what it really comes down to is when you should use one over the other is when we're talking about the shape of data distributions. So yesterday we talked about normal distributions, or sometimes they're called bell shape. And things that have normal distributions, heights of people, standardized scores, a lot of things take on normal distributions. And it turns out we're going to find out that even if you don't have normal populations, there's things we could do that are going to make them look more normal. So the other types, though, that we'll see sometimes is skewed distributions. These are pretty common. So you can have skewed left distributions, or you could also have skew right. And in a skew left distribution, looks something like this. Okay, and so this is what we call, say, like the tail of the distribution. So whichever way that tail gets stretched out, that's the way we say the skewedness goes towards. So notice that in this distribution, there's most observations are piled up here at the top, and it kind of tapers off down to the bottom. Okay, so then skew right's kind of just the opposite. You have that kind of effect where most things are piled up down at the bottom, but it tapers off to the top. So the thing about skewness is that it basically, these skew distributions, they sort of have like built-in outliers. So in a skewed right distribution, you don't see a lot of people up here, or a lot of things up in these high observation levels, but they happen, and they're definitely part of the distribution. They're just not very common. Okay, so we came up with some examples of these actually yesterday. What do you think are some values that you could record or data you could take that might have a skewed left distribution? Yeah, so age at death would be something that probably has a very skewed left distribution, right? Because the majority of people will die up here somewhere past 50, 40, 50, right? Of course, you see people die at younger ages, but it's not very common, right? Would definitely have a skewed left distribution. What else? Can you think of any other distributions that might be skewed to the left? Most of the observations are up high. Yeah, so probably, well, age of marriage, I don't know. Like age of first marriage? Okay. Well, I mean, what's that? Well, hold that thought for a second. But because I want to think about this, the age of first marriage, say, of Americans, do you think it has a skewed left distribution?
No.
I would say it was skewed right.
Yeah, skewed right.
I would almost be tempted to say skewed right, because probably the majority of Americans who get married, their first marriage probably happens, before the age of...
Skew left could be age of second marriage.
Age of second marriage? Probably, yeah. Probably the age of first marriage, like, I would think it probably is... I'm not saying everybody has more than one marriage, right? I'm just saying that for people multiple, but yeah, age at subsequent marriages beyond one would probably actually be the opposite. It'd be skewed to the right. Or skewed to the left. Yeah, I think it'd probably be skewed right because the majority of Americans who get married, they probably have their first marriage by the time they're in their mid-30s, ish, right? But there are people who might not get married until much later in life. Either one, okay, left or right, what do you think? I heard other ones, but I forgot what.
Would be like income.
Yeah, so definitely incomes in the U.S. In most countries. But yeah, incomes are very skewed to the right. Most of us are down here, less than 100,000, less than 150,000. But occasionally you see people earning way, way more than that. What else? Can we think of other skewed left ones? I think someone might have said one. What did you say, Brittany?
College tuition.
You think so?
Yeah, it's definitely rising.
It's rising, but remember, this isn't measurements over time, right?
Oh, it's not.
Remember, this is like I'm just recording a whole bunch of data, and then I'm making a histogram, right? And so this is like the shape of that histogram that's being made. So it's like I'm just measuring one thing about a lot of people. Or so if like in your example of college tuition, I would just be going to a whole bunch of colleges and seeing what their tuition is, and then where do you think the majority? What shape do you think college tuition is? Probably, actually,
Bell.
it could be pretty bell shaped. Could be. I think actually I saw a data set on this one time. It turns out, I think, if I remember correctly, college tuition tends to have what we call a bimodal distribution. So since you mentioned it, you can have distributions that have more than one peak. Yeah. So it turns out in terms of distributions for like college tuition, they actually have a shape kind of like that about-ish. Because what you see here is down here you have like the 2-year colleges right there. And then up here you see a peak around the average cost of 4-year colleges, right? You don't see quite as many in between. And this peak is higher than this just because there's way more 2-year institutions than there are 4-year institutions. Yeah. So it's actually kind of bimodal, and it's a little skewed to the right-ish. Because most colleges, only because of the overwhelming number of 2-year institutions compared to 4-year institutions in the country. So it kind of swamps the 4-year. If you just looked among like 4-year institutions, it'd probably be a little more symmetric, or 2-year institutions would probably be even more symmetric than that. If you just looked at 2-year colleges. Yeah. So you can have multimodal distributions. We're not going to really deal with that kind of stuff. What else do you think could be skewed? We can come up with something else that's skewed left.
Average American debt.
Average debt? Debt of Americans? Like what kind of debt? All debt? You think most of us have a ton of debt and only a few people have no debt?
I think it's getting up there.
You think so? I'd be interested to know. I don't actually know. I couldn't say with any confidence, but it could be. Especially if you looked at maybe college graduates. Yeah, especially if you looked at people who say graduated from college in the past 12 months, recent college graduates. It could be like that. Yeah, I think the majority of college graduates have some debt. I don't know about that. Yeah, I'd be interested to know that. I don't know what it looks like. How many Americans carry debt? Yeah, and like they want you to pay those back apparently. I just found that out. So, yeah, that's something to think about, by the way, just so you know. It's just about every $5,000 you take out in loans, that's a $50 a month payment when you get out of school, just so you know. By the way, something to think about while you're taking out loans. So if you take out $15,000, be ready for a $150 a month payment when you get out of college. And they're not very lenient about that, apparently, so.
When they want their money, they want it.
Yeah, okay, I get it. Anyways, so can we come up with something else that's skewed left? I think that one could qualify, especially if you looked at a really specific subset. What else? Can't think of anything else. The milestone kind of ages, like age at retirement as well, things like that. What was one I could think of? Nobody can come up with anything else. We can come up with one other one that's skewed left. I feel like we can definitely do that.
Miles on the car?
Like on a certain year?
Yeah.
Yeah, probably the mileage on a vehicle of a certain age. It probably is. You know, most people are going to be up towards the top limit of how many miles you could possibly drive in that many years, you know. But there are going to be people who just don't drive their cars that much. Yeah, I think that's true. Okay. You guys get the idea? Make sense? Cool. So what's the point of knowing what your distribution looks like? The idea is that depending on what your distribution looks like, it's going to be more or less likely to affect the mean and the median. So the nice thing about The nice thing about symmetric distributions is that if you have a symmetric distribution, then your mean is going to be pretty much exactly the same as your median, right? Because the mean's going to be right in the center because you have the big values canceling out the small values, and there's an equal number of them. And the median's right in the center anyways because that's what the median is, right? It's the halfway mark, where half your distribution's below and half your distribution's above. So in a symmetric distribution, they're pretty much the exact same. The thing that happens, though, when you talk about skewed distributions is, so say that I have a skewed right distribution. Remember, which one is more affected by outliers or extreme observations? The mean. So what's going to happen to the mean in a skewed distribution? Where are our outliers in this distribution? Are they at the bottom or are they at the top? They're up here, right? Most of us are down here. There's a few extreme values or outliers out here at the tail. And so what's going to happen towards the mean? Which way is it going to get pulled? It's going to get pulled towards the tail. Yeah, so your median might be right here, right? But your mean is going to get pulled up. So it gets pulled toward the skew. Okay, pulled towards the skew. And similarly, if you had your skewness the opposite direction, you know, your median might be here, but then your mean is going to get pulled down. Down. Yeah? Now, what this means though is that you need to be careful what values you report or what values are being reported. So, for example, I was just reading an article actually just today, and they were talking about real estate prices in the area, and it was saying that the average real estate price has gone up like so and so many dollars over the past year, like year to year, closing prices. And they were talking about the average of home values. But what do you think is a more accurate measure of the middle of home prices, the median or the mean? Why? What shape do, here, let me add a slide here. What shape do you think home prices have?
It's probably skewed, right?
It's probably skewed. So let's think about here. So think about home prices. Home prices are probably pretty skewed because the majority of homes, you know, in the area are going to be under a certain threshold, right? And it would be skewed for each city in particular, but even overall, what's probably an upper limit on the majority of houses, like the large, huge chunk of houses in the area? Yeah, probably by the time you hit like 300,000, you've covered a pretty large chunk of Tri-Cities real estate, would you say? And so, of course, are there neighborhoods where there's houses that cost $400,000, $500,000, $800,000? $1 million? Sure, they're out there. There's not that many of them, but they're out there. So yeah, I think it's skewed to the right. Now, if you're thinking about that though, so if I tell you the median home price and I tell you the mean home price, which one's going to be bigger? Yeah, so the mean home price, the median is going to be smaller. But which one of those numbers is actually a more accurate representation of most homeowners in the area? Is your home more likely to be close to this value or this value? Yeah, your home is more likely to be close to the median value. It's way more reflective of the actual situation of home prices in the Tri-Cities, right? This mean is being inflated by that $3 million house on 20 acres or something, right? This means getting dragged up by some of those houses that are selling for $750,000, $1 million, and it's not really accurate representation of what most home owners or home buyers or home sellers actually experience. So then, and typically the rule of thumb is that if you have a symmetric distribution, then stick with the mean. And the reason we say that is because we're going to learn a lot of really nice qualities or a lot of things we can do with the average. But if you have a skew distribution, then the median is a much more accurate representation of the population as a whole. So when you read an article and it reports the mean or it reports the median, you can think about, is the average really the best thing to report here? That mean price is going to make houses look a lot more expensive in the Tri-Cities than they really are. Or at least a little bit more expensive than they really are. Because the mean could go up if only the most expensive houses in the Tri-Cities, if only those values were rising in prices, that's going to inflate your mean, but it's not going to inflate your median. Make sense? Yeah? Cool. Just something to think about. Okay, so those are our measures of center. We deal mostly with mean and median. We have some different measures of dispersion. So another way to think of dispersion is sort of like the spread or the variability. Okay. And the most common ones we usually use are things like maybe we'll use the range. We'll use something called a standard deviation. And we'll use something called quartiles, but those will kind of help us look at the spread of data as well. We'll go into each of these, though. All right? If you're working ahead at all, you may have already had some experience calculating standard deviations. They're pretty fun. All right? So the range, pretty straightforward. So what is the range? How do you calculate the range of a data set? You may have had experience with this. What do you got? How do you calculate the range? Yeah, you just say what's the maximum value, what's the minimum value, and how far does it take to get from one to the other? Right? Okay. The only problem with the range is that if you have some data spread out and say here's your min and here's your max, well the range doesn't give you a lot of information about how that data is spread out. So maybe the data is like uniformly split, from one to the other, or maybe the data is bell-shaped, or maybe the data is skewed, right? We don't really know, but it tells us something. Okay. So we do use that as a measure of variability or dispersion. So here's a selection of 9 students, and they recorded their pulse rate, right? So we looked at this data earlier, I think. So what would be the range of their pulses?
60 to 86.
Yeah, so their range is, the low is 60, the high is 86. So we would just do the difference. So their data has a range of 26 beats per minute. Yeah? Right? Pretty straightforward. Cool. So just take the max minus the min. All right. All right, so the range is great and all, but it's really not that cool, and we don't really actually use it at all in statistics, so you can just forget it ever happened, kind of. But anyways, it's something you'll see sometimes. So the standard deviation is really sort of like the gold standard in statistics for measuring dispersion. I'm trying to think how I want to enter it, if I just want to give you the formula. So here's the formula, all right? Let me see what I got going on here. Sometimes I forget what I wrote. But what the standard deviation is going to attempt to do is our goal was to measure how far on average the data is from the mean. So we wanted to get some idea, some measurement that would allow us to say, okay, is the data really all close together, all really close to the mean, or is this data really spread out? So you have things way low and way high. And so the standard deviation is what we came up with. And this is what the standard this is the formula for the standard deviation. So, all right, here. So to calculate, say, a sample standard deviation, here's what we did. So normally the sample standard deviation we denote with a little s. Okay. So the first thing we do, right, so if we're trying to measure how far observations are on average, the first thing we do is we go in and we take all of our observations and we subtract the mean, right? So these are like the deviations, like how far is each value from the mean? You know, are you 10 beats per minute above the mean? Are you 9 beats per minute below the mean? But the problem with that is that, remember, the average, if we're going to average something out, there's always like some summation involved, right? So some people are below the mean and some people are above the mean. And if you look at all their deviations, you're going to have a bunch of negative deviations and a bunch of positive deviations. And if you add up a bunch of negative and positive numbers, what's going to happen? Probably. They're going to all cancel each other out, and every single time you go to calculate a standard deviation, you're just always going to get 0. So that's a problem. So what we needed to do is we got to figure out, okay, well, how do we make all those deviations positive? Well, what's one way to make everything positive? What's one way to turn negative numbers into positive numbers?
Yeah, multiply by negative.
So yeah, so we could do absolute value. Okay, it turns out absolute values are nightmares. Okay, so we just hate absolute values. They're the worst, basically. And so what's another way you can turn a negative number positive? You can multiply it by another negative number. You could also do what? What other operation makes things positive? You could divide it by a negative number. But then we'd have to choose what arbitrary number we want to divide everything. And we can't really do that necessarily because what if it's a positive number and then you divide it by a negative number? Oh, crap, now we just made all the positives negatives, the negatives positive, now we get the same problem. So what's another way we can make them all positive? What's that? Yeah, something with themselves. So you could maybe multiply them. I think multiply. Yeah. So if you square a number, doesn't it make it positive no matter what it is? Yeah. So that's what we do is we take all these deviations. So some people are below the mean, some people are above the mean. So we just square them all because then the positive ones stay positive, the negative ones stay negative, or the negative ones turn positive, and everybody's positive. Now we can add them up and we get a value. And then this is going to be weird. We end up dividing by n minus 1. Seems kind of counterintuitive. Okay. And then you take the square root of all that. So. All right. It turns out there's a lot of intuitive interpretations to the standard deviation. So it's really not arbitrary. Okay. We can interpret this very nicely, and we're going to do that. We're going to use the standard deviation all the time in this class. Okay. But this is the actual formula for a sample standard deviation. Okay. So you might anybody have any questions about that besides what is this gibberish? Yeah. Okay, so we're gonna do some examples where we'll learn how to use it. Now we do differentiate again, right? We have the population versus the sample. So in the population, right, there's always a parameter versus the statistic. So as we just saw in that last slide, we call the statistic S, right? So that's the sample standard deviation. The parameter, though, we call that a sigma, a little sigma. Okay? So this is what we call the population standard deviation. So I'll leave that over here. That's the notation we use. Okay, and actually their formulas change a little bit because so say that you actually knew your whole population, right? Then you could calculate the actual variant, the actual standard deviation, like the real standard deviation. It would be a similar formula, but you would be subtracting off. If you had the whole population, you would know the actual mean, not just the sample mean. And you would actually only have to divide by the sample size, the actual population size, because you'd have the whole entire population. The sample standard deviation is where you have to have that weird n-1 in the bottom. And of course, if you're dealing with a sample, you also wouldn't really know the population mean, so you just use the sample mean instead. Okay, but they're almost identical formulas. It's just whether or not you have everybody or you took a small subset of everybody, right?
So everybody's a top one?
Yeah, this would be like this. So this is right. This is the population. You know, and in reality, we never really have this. If you have your entire population, then that's not really typically what statisticians are interested in, because if you have the population, then you could just know everything already because you've already seen everybody. But typically, the sample is what we're dealing with. Okay.
Wait, so the bottom was supposed to be -1?
Oh, good call. Yeah, yeah, it's supposed to be an n-1. This is kind of a weird thing. This is actually something that we call the degrees of freedom. Which would make a really great name for a boy band. So I really like saying it. But we're going to get back into degrees of freedom later on in this class. The idea is basically when you're taking a sample, notice that this right here is the sample mean, right? So if I have a bunch of observations and I know the sample mean, so let's say I have I sample 30 cars, right? And if I tell you the mean and I tell you the value of the first 29 cars, do you know what the value of the 30th car has to be? Could you solve for that? You could, right? Because if I give you the 29 cars in the average of all 30, you should be able to solve for the 30th car's value, right? So in a sample, because we've already estimated the mean, the only 29 of those variables have any freedom, because once you fix the first 29, the 30th doesn't have any freedom at all. It has to be what it is, like it's fixed. And so that's why the degrees of freedom is one less than the sample size. It's not really something you need to know, but that's kind of the explanation for that. But anyways, we're going to move on. Okay? All right. So calculating them, though. All right. So let's see how to actually calculate them. That's the hardest part. But it ends up being pretty easy if you break it down. So I want to calculate a standard deviation. The way I do these, if I'm going to do them by hand, is I do them with a table. So I list out first all the observations, and then I go step by step along my table. So you get 76, 60, 60, 81, 72, 80, 80. Oh, I'm out of room. 86. That's okay. 73. Okay. So I write down all my observations. Should left myself a little room here. Maybe I did. Oh, I did. Blah. Whatever. Okay. Yeah, you can finish copying that table. I'm going to do it over here where I got more room. Can you guys give me the numbers again?
76,
Mm-hmm.
60, 60, 81, 72, 80, 80, 86, 72.
What was it, 73 at the end?
Yeah.
Okay. So we were going to walk through our formula step by step. Okay. So remember, I'll put it over here so we have it. Our formula is the sum of the observations minus the mean squared all over n-1, and then you take the square root. So I think in this one I said assume this is a sample of a larger class. So we're doing a sample standard deviation. So right here what we're going to do is the first thing we need to do is we're going to take all those observations and we're going to subtract off the average. So we also need to know the average, which I think we already calculated. Didn't we already do that? What was the average before we threw in the outlier? Was it 74.2? Or was that the median? No, that couldn't have been the median. I think that was the average. 72.4? Is that what it was? Let's look. 74.2. Okay. So the first thing we'll need is that. Okay. So that's the average of our 9 observations. So the first thing we're going to do here, following our formula, is now I'm going to take that and I'm going to subtract it from each of these, right? So we're going to do 76 minus 74.2. We're going to do 60 minus 74.2. 60 minus 74.2. Dot, 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 dot. All the way down to 73 minus 74.2. Okay? And we're going to figure out what all of those are going to come out to be. Okay? So 76 minus 74.2, what is that, 1.8? Okay? 60 minus 74.2, that's a negative 14.2. 60 minus 74.2, that's a negative 14.2, I think. 81 minus 74.2, what's that, 6.8? Okay, 72 minus 74.2, what is that, a negative 2.2? 80 minus 74.2, I think that's a 5.8, which means this is 5.8. 86 minus 74.2, what is that, 11.8? Ish? You guys can check me on this. I'm doing it in my head, which means I'm probably wrong. 73 minus... Okay, and then this one would be, what, a negative 1.2?
Yeah.
Okay, all right. So these are all those deviations that I was talking about. Right, that's the raw numbers. And notice there's a bunch of negative numbers and a bunch of positive numbers. And if you add them all up, you're going to get something pretty darn close to 0. Right? So that's useless. So instead, with our formula, what does it say we need to do? Yeah, we need to take all those observations and square them, right? That's our step that we need to do in our formula. So now I need to take that 1.8 and square it. I need to take negative 14.2, square it, negative 14.2, and square it all the way down, square all of these, square that, and we'll get all our squared deviations. Okay? So this is where you guys are definitely going to need a calculator to help me out here. So pull out your calculators. What is 1.8 squared? What is it? 1.34. It should be bigger than 1.8, shouldn't it? I think it should be closer to 4.
Oh, no, my nice square rooted it.
Yeah, 3.24. Okay. What's 14.2 squared?
Negative 14.2
Yeah, well, either way, because it's going to turn it positive.
1.64.
201.64. Other people get that? 201.64. So this one's also 201.64. What's 6.8 squared? Remember, this is 6.8 squared. 46.24. Okay. 2.2 squared. Yeah, still be positive, right? So what is it? 2.2 squared is what? 4.84. Okay. How about 5.8 squared? 33.64. Which means the next one is also 5.8 squared, so that's 33.64. 11.8 squared? 139.24. Other people get that? Okay, and then what's 1.2 squared? 1.44. All right. So these are what we call the squared deviations. Again, you don't need to know this probably, but I'll write it there just for kicks. Okay. Now we got everything positive. Now notice also too. So some of these values, when the deviation is really big, by squaring it, what do you do to it? When you take a big number and square it, what do you end up with? An even bigger number, right? Whereas like 1.2, when you square 1.2, it doesn't really change it that much, right? And so one thing the standard deviation formula does is it kind of like penalizes values that are further away from average. So the bigger your deviation is, then when you square it, it gets even amplified. Whereas if you're really close to the mean and your deviation is really small, well, when you square that, it doesn't get very amplified. So it's kind of punishing those values that are really far away. And so it's saying, hey, that value is really far away, so that really needs to increase my variability because it's showing me there's things way out there. Okay. Okay, so we have our squared deviations. Now what do we do with them according to our formula? Almost. First, we need to take care of that sigma, which tells us to add them up, right? So now what we need to do is we need to take those values and we need to get the sum of those squared deviations. So we need to take that 3.24 plus all the way down to 1.44. Okay? So I'm adding up every single one of these values. Actually, you're adding up all these values. And we're going to see how many people we can get to agree on a number.
I got 665.56.
Okay? Anybody get that or something different?
Yep.
What did you get?
Ditto. The same thing.
665.56?
I got what you got.
Perfect. Okay, so if you add those up, you should be able to get 665.56. That's the sum of our squared deviations. So now what does our formula tell us to do? Divide by n minus 1. So we're going to take that number and divide by n minus 1, which means we're going to take that 665.56 and divide it by, well, what was our sample size here? How many people did we talk to? Yeah? So we're going to divide by 9 minus 1, which will be 8. So what is 665.56 divided by 8? Give me that one.
83.195.
83.195? Okay. And you divide it by 8, correct? Okay. All right. So now what's the very last thing we need to do? Yeah, we need to take that number. We added up the squared deviations divided by n minus 1. The very last thing we need to do? Square root. And that's going to be the square root, so the square root of 83.195. And that's going to be about what? 9.12. And the units are the same units that the actual data was in. So it was in beats per minute, because we're talking about pulse rates. So the standard deviation is 9.12 beats per minute.
That's a lot of work. Just on beats per minute.
I mean, a lot is a subjective term, right? Because that took, yeah, it takes about 3 to 5 minutes. Okay. Depending on your data set size. You get a way bigger data set now, it could take a lot longer. Okay. There is actually, I'll show you, there is a shortcut in a sense. Okay. So there's another formula that you can use. And now I'm wondering if your book even uses it, but I'm going to use it. Because it does make it a little faster. There's something called the computing formula. Okay, and an alternate form for it works at least for the sample standard deviation. It says you can take the sum. Oh crap! It's the sum. I forgot it now. I think it's the sum of the x squareds minus the sum of the x's squared over n, all divided by n minus 1. Now that actually looks like it might be more complicated, right? But it actually involves less calculations. Because notice that we don't have to use the mean at all. There's no like x bar in here, and there's no subtraction. So all you need is the values and the values squared, right? So I'll show you how this works real quick. And let's get our data back. So it was 76, what was it, 60, what were the other ones?
81.
81,
72.
okay.
80.
Uh-huh.
80. 86.
73, okay. So we have all of our x's, and then all we do is we just square those. So what is 76 squared? So I'll need you guys' help again. 5776. Yeah, just get you can just give me the digits. What's 60? Oh, 60 squared is what? 3600. Okay, 81 squared.
6,561.
6561. Okay. 72 squared.
5184.
5184. 80 squared is what? 6400. 86 squared.
7396.
7396. And 73 squared.
5329.
5329. Okay. So now notice this one doesn't need as much stuff. It only needs the sum of the x's and the sum of the x squareds. So what is the sum of the x values? So what's the sum of all these? So if you sum up all the observations themselves, 76, 60, 60, 81, 72, blah, 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 what do you get? What's the sum of all those? Anybody got one? A number for that? Just throw them out there. We're liable to agree on some of them.
47.
What's that?
That was a joke. I was joking.
47.
You said just throw a number out.
I didn't say everyone's numbers will agree. Yeah. What is the sum there?
668.
668? 668? 668? Yes? No? Maybe so? People disagree?
Sure.
Anybody else get it? 667?
I plugged in that wrong.
668, I got again.
I'll agree with that.
Anybody else got it? No? I'm going to write it down.
I'll agree with that.
Yeah, I think it is 60. I think it's got to end in an 8. Just looking at the numbers. What about this one, the big one? Add that one up and tell me what you get. That was going to be really fun. 50243. Anybody else get that?
That's what I got.
50246, 50243, 50246,
I got 50243.
50243. Oh, this is about to get ugly. We're going to have a fight. Let's see. What is that last digit? It has to be 6 and 4 is 10, 11, 17. I think it has to be a 6. It has to end at 6. Probably just an input error. I think it has to be a 6. Anybody else get that? 50046. Oh no. I'm waiting. I can wait a long time. 50246. I'm getting more. Okay, I'm getting confirmation of this. I'm going with that one. We're going to be able to figure out pretty quick if it's wrong, because we'll get a different answer than the original. Okay. 50246. 50246. Okay. So all you have to do is sum up the x values and sum up their squared values. Okay. So and then in this formula, then you just plug in those values in. So the sum of the x squareds, that was 50246. The sum of the x's was 668. So we're going to end up squaring that and dividing by the sample size, which was 9. And then downstairs we have 9 minus 1, which is going to be 8. Okay. So here we'll get, what's 668 squared and then divided by 9? Just do it in one step for me and I'll just get that number.
49580.44.
668 squared divided by 9, you got what?
49580.44.
Anybody else get that?
Yeah.
Okay, so it was 49580.44 ish. 4s go on forever.
They got 4 digits.
Okay. And then down here, you got an 8. Okay, so now take 50,246, subtract that number, and divide it by 8. And what do you get under the square root? So take the big number minus the little number, divide by 8.
83.19445.
194. Anybody else get that? 194 dot dot dot. And what's the square root of 83.194? That number should look familiar, actually.
Square root of that is 9.121.
It worked. Yeah. So we got the same answer that way. So the computing formula, I think, is actually a little faster. Maybe by a minute. But it does leave you a lot less room for error, because notice we did a lot less calculations in this one. Because in the other table we had multiple steps where you had to subtract it, then you had to square it, and then you had to add them up. Whereas here all you have to do is square them and then add them up and plug them into your formula. Yeah? So you got to be able to do it one way or the other. But it gets better, at least from a homework standpoint, because we have these wonderful things called computers, right? So you can actually do this in StatCrunch. I'm going to show you how. So in StatCrunch, and remember, you can open all these data tables in your homework straight into StatCrunch. Ish. Well, maybe if it's going to start up for me. Come on. Don't do this to me. Hey, welcome back. What the heck? Maybe it's not going to work today. Am I still logged in? Yeah, I'm still logged in. Oh, here it goes. Okay. Come on. My network connection is not very good. So like, let's say here, I'll put my pulses data in here. So again, I'm going to need those numbers, but I'm almost, 76, 60, 60, 81, something else?
72, 80, 86, 73.
Okay, so there's my pulses. So this is actually, I was showing you this function, I think, a couple days ago. In the stat menu, there's a summary stats. So summary stats for columns. And when you select that, it's going to give you a whole bunch of options. The first thing you do is you just tell them where your data is. So we're looking at the data in the pulses column. And then right here, you can pick all sorts of fun things to compute. But like, say, for example, we calculated the mean and we calculated the standard deviation. Then you can just hit compute and boom, there you go. There's your mean, 74.2. Here's your standard deviation, 9.12, and everybody's happy.
So if we use this for our activity 2, will it graph it for us?
Sure, you can graph it if you want.
Tell us your graph.
Yeah. So this gives you your mean and standard deviation right away. Done. That helps you for your activity. Again, that's in summary stats for columns. All right.
Can you show how to graph?
Yeah. So the graphs are all in the graph menu. So say you want a histogram for this data. I want to see the histogram for my pulses. It's going to be a little uninteresting because I only have 9 observations, but we might be able to see something. So you click histogram, and again, you just pick the column you want to graph. So I want to graph my pulses data, and I hit compute, and there you go. Got a nice histogram of my data. This is pretty uninteresting, only because I think we just don't have enough data here. That's one thing to consider when you're thinking about taking data for, say, your cars. If you want to make a graph, I mean, you really need probably 20 or 30 observations to make a really interesting graph, because 2 or 3 just doesn't make a very good graph. But again, that was in graph histogram. So the other stuff was in summary stats for columns. Yeah, and you can actually compute all sorts of stuff. So it was mean and standard deviation. You know, we did the median earlier. It'll, I didn't pick the column. So it'll spit out the median for you as well. The median was 76, right? And so you can pull your data in from your homework. And from your homework, you know, it's really quick because you can just hit that option with the table drop down where you just say open at StatCrunch. So now, granted, you need to be able to do it by hand at least once. Okay. So my recommendation would be when you're doing the homework, calculate it by hand first, and then use StatCrunch to check it. Do that a couple times until you're comfortable doing it by hand, and then I would just use StatCrunch because it's going to save you a lot of time. Okay? All right, that's where we'll pick up tomorrow.